Hello, 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 hello. Hi all, very good evening to all. So we'll start the session now.
Good evening, ma'am.
Yeah, good evening, Kush. So actually there was some issue in my mic, so it got late a little bit. Yeah. So everybody has registered for the exam. Kushit, have you registered?
Yes, ma'am.
Okay. So here we will start week 7. Week, okay. Mic, okay. Share screen. So yeah, I would, and my voice is clear, right? Hello, just
Yes, ma'am.
confirming. Okay, okay, thank you. So yeah, so we will start this week 7, and we will solve some questions related to week 7. So I guess your exam, can you tell me when is the exam? We will practice accordingly then.
Ma'am, on 29th or 30th of April, 30th of April.
April. Okay, okay. So right now today is 18th of March. So next week and next week I can take some weeks. Then after that we will only solve questions so that you will not have any issues. And I want that for you you can score well. So we will just solve questions and see how you are performing so that you can have the best marks. So yeah, to 18th and then next week. I'll just deal with some week 7, week 8, week 9. I think 11, 12th I won't deal. I'll directly solve some questions related to your exam so that you will have better understanding. So in this week, the professor has introduced the pulse amplitude modulation, sample and whole circuit, and flat top sampling. So in the last week we saw that the impulse sampling and how the flat top sampling is different from the impulse sampling. So yeah, so in pulse amplitude modulation, which is a PAM, it is a digital modulation technique where we use sample and hold circuit and the sampling process. So in the ideal modulation, ideal sampling, what you have the time domain signal like this, and in the impulse sampling, you will multiply it to the impulse train. So that was the ideal sampling. But here in practice, we don't have ideal sampling kind of stuff. We usually multiply it with a pulse train. So we have looked in which we have signal and it is sampled using an impulse train. Where, but here in pulse sampling we will multiply using a pulse like this. and we will get these message signals, free multiplication of MTS, where n ranges from 0 to n minus 1. Periodicity it depends, or somewhat it can ranges from the minus infinity to infinity, because summation we will have minus infinity to infinity, 1 by Ts m f minus n fs as an output of sampled frequency domain signal. So here you can see n can range from minus infinity to infinity. Now, how we will solve using the pulse? So the nth pulse, I think, yeah. So duration of the pulse, the sampling using a pulses of duration at each ts at each nts where the duration is t. So how this will look like? Whereas the sampling at each nts and the holding the sample value to constant for duration t. Here what we were doing, we were having this message signal and we were taking only at some nts value, but in the pulse sampling we will hold the same amount for the time duration of t. So there is a difference, but the criteria should be t should be less than ts, so that we will have the infinite samples, otherwise we will not have. So the pulse duration should be less than equals to less than ts. What if it is not less than equals to ts? What will happen? What will happen?
Ma'am, we won't get those many samples of this message signal. If pulse duration is too much.
For example, this one is
Yes, ma'am.
t. So this is in time domain. What will happen in frequency domain? In frequency domain, we saw that you only derive the expression equation, right?
Yes,
So
ma'am. Multiple sync function will be there. We won't get any perfect message signal.
yeah, multiple single function will there, and we will get at the end only distortion. So this should happen. Now, so I think sir has solved this flat top pulse, hence known as flat top. Implies flat top pulses, hence known as flat top sampling. So this is what after flat top sampling we will get a pulse amplitude modulation. So difference is, whenever the modulation term comes, so we don't require the modulation to be at the baseband frequency. We require the modulation to be at higher frequency so that the antenna size reduces, and we can actually transmit it to a higher distances, so that we'll have the carrier. We require carrier that is having high frequency fc should be greater than or equals to fm. So after sampling, when we do modulation, the amplitude modulation, we will call it as a pulse amplitude modulation. No, but yeah, the message signal will have these type of variation when it is multiplied with this. And this the sampling sometimes is also called as sample and hold circuit. So please don't the confuse between it, because we are doing sample for this period and then hold, then we are doing this sample for this period, then we are taking hold, and then again and again, so that we are getting samples. And what is required at the receiver, the minimum number of samples required to reconstruct the original this one message signal is called the sampling theorem, or the Nyquist criteria that we solved. Fs should be greater than or equals to 2 fm. So that was the case. So it is the minimum number of samples required. So how many samples the sampling frequency should be? So here it is required like this. Now PAM refers to, I think this is very, you have for ideal sampling one has to generate a train of impulses, which is impractical. So that's why we are what we are doing. We are just it's rather a representation of generation of PM. So we are not doing the generation of impulse train. Rather we are taking the generation of pulse. Why pulse? Because pulse is a harmonics of sine and cosine. what we write pulse as a harmonics of sine and cosine. So sine and cosine are natural occurring analog signals. So these are actually practical. But yeah, impulse is not practical. But for the better understanding, what we did is as a impulse signal. So this one is after multiplication with a pulse train. This one is a pulse amplitude modulated signal. Why pulse is it is taking as a amplitude modulated? Because here the pulse train is having higher frequency than the message signal. The frequency variation is there. Then Sir taught about the spectrum of band signal, reconstruction of original signal from the equalization. The similar equalization we did. We did the equalization filter in the form of sync. HT was in the form of sync function.
Yes, ma'am.
Yeah. So similar equalization you will also receive here as a sync function for sure. Why equalization is needed?
Ma'am, because there is distortion of this message spectrum because of this sync function. So to correct for that,
Yeah, yeah,
phase
yeah.
distortion and amplitude distortion as well. Phase distortion by 90 degree and amplitude distortion by whatever the magnitude of this sync is.
Okay, nice, nice, nice. You have read then. Yeah. Though, so can you tell me this output? This one is
What is this?
LTI, and
Okay.
suppose you have A sine omega t, then what should be the output of LTI?
Ma'am, what is it's that impulse response of
No, no,
LTI?
no. Any impulse response HT. Yeah, you can
Yes,
say,
ma'am.
but it is just a
Magnitude and
convolution.
phase will change. Magnitude and phase will change
Yeah,
as per
yeah.
this
Yeah, I am
response.
saying that the sine sinusoidal term
Yes, ma'am.
remains same. But yeah,
Yes, ma'am.
the magnitude and the phase will change. Amplitude and phase will change. So what it implies here? The sinusoidal nature never changes behavior when passing through the LTI system. And what we have in practice is LTI system. For example, you can take integration. Integration itself a LTI, differentiation is itself a LTI, and the phase modulation itself a LTI. So you will have all these system as a LTI. So that's why we refer this as a LTI system. And one more thing, whenever we talk about a transfer function, we consider the initial condition of an LTI system to be zero, right?
Yes, ma'am.
So HF, or we can call it HZ, if it is in the terms of Laplace transformation, then it will be ys by xs provided x0 is equals to 0, and here yz whereby xz provided x0 is equals to 0, means input initial condition of the input should be 0. So why I'm taking this criteria to be here and this concept to be here? Because in every equalization also, you saw the equalization process itself a LTI system. You can map it to a LTI system. I think Kushit, did you have you given the gate paper this time?
Yes, ma'am. Actually, I am thinking of taking admission in IIT this year for MTech.
What is your gate score?
Ma'am, it is gate score is 526, and I am from OBC category.
Okay, okay, okay. Nice, nice, nice. Congratulations. Like you have cleared with a good rank. Can I know your rank also?
Ma'am, 1100 something it
Okay,
is.
1000. Okay, then you can definitely get and take in at least IIT. In fact, you can apply to IIT Hyderabad, some smart
Okay.
mobility branches and all. But
Yes, ma'am.
it's a good opportunity that you can apply. Yeah, and then so in the gate questions you have since you have given the gate exam, so in the gate question, I think this year itself, they have asked this LTI system,
Yes.
the equalization. Did you saw the equalization question here itself?
No, ma'am, I don't remember
Okay,
about
you don't
this.
remember, but yeah, the professors of IIT mapped the equalization to a LTI system, and then
Okay.
they have asked the question. So here
Okay.
the similar equation you have must have got like sync function. I'm damn sure about it because it is required to reduce the distortion. And then the equalization was mapped as a LTI system. And why LTI system? Because LTI system is a naturally occurring system we found in everyday life, because integration, differentiation, and in many analog circuits also you have seen analog circuits as LTI system, like R3 we saw envelope detector, that also we can map to a LTI system. The input and output, if you have input as a sinusoidal and an output as also as a sinusoidal. So we'll see the equalization, how the equations look like. So pulse amplitude modulation, MT, if you have MT and delta t, when you have impulse sample signal, you know that this is the expression for that. Then after this expression, the impulse sample signal, the pulse amplitude signal will look like if you have mapped it to a pulse signal. Instead of delta, you will have the pulse. So MTS, MNTS, P, T minus NTS. Now, what the frequency domain of this one looks like, how it will look like. The similar expression using sync function it will have, because what we'll do here, the multiplication, we will write this as a Fourier series, and then Fourier series will convolve it to this M. First, what we'll do, Fourier series representation of pulse of P T, which is a periodic function. Then what you'll do, you'll do convolution, and the convolution you have the property, and then third, what you will have, a shifted
Spectra.
sync spectrum. So this you always remember, first you have to do the Fourier series representation, then convolution, and then spectrum. So here we'll see ht for suppose a pt. So the similar expression you might have got also. So this one, mnts in convolution of pts. Why this is blur? Okay. So finally, this you know that this convolution in time domain is simply the multiplication in frequency domain. Then if you have no aliasing, then fs should be greater than equals to 2 fm, and then similarly sampling frequency, no aliasing, and then delay by 2 t by 2. So you remember this one now. Uh, this will have a tau sync f tau, which is a t minus t by 2 to t by 2. And similarly, if you have just shifted version of it, this one, all will have sync only. So one question I ask from you, what is a sync? Suppose sync 100 tau, 100 t. What should be the sampling frequency of this fs?
Sampling frequency of this sync function.
Yeah, this is a time domain sync function, and you have to find a sampling frequency. Then we will
Yes,
find.
ma'am.
Yeah,
It's
yeah.
quite simple. It will be uh, Fs by 2. Fs by 2. Yes, ma'am. It should be 50 hertz.
No, no, sampling frequency. I'm asking sampling frequency. FS.
Should be 100.
Yes, yes, yes. Nice.
Okay.
It should be 100. Why 100? Because if you just Koshid, before going to anything now, first try to make it as a frequency domain. Frequency domain, if you'll make, you will have here what you will have
Yes, ma'am. Got it, ma'am.
100. Okay, 50, 50 and minus 50. So frequency domain, the bandwidth is FM is equals to 50, and FM should be 2 FM.
Two times of this.
Yeah,
Yes, ma'am.
100. Similarly, I'll ask sync. This is the favorite question of gate. Like everywhere, this year might might not have got, but yeah, I
Yes,
have
ma'am.
seen many questions of sync square.
Yes, ma'am.
Um,
I got it. Triangular pulse.
yeah. So what should be the sampling frequency of this?
It will be 200, ma'am. Now bandwidth becomes 100.
Yes, yes. Nice, nice. So what should be the sync NT?
Yes, ma'am. On similar lines, we will have that.
100n,
Um,
right?
yes, ma'am. Yes,
Right?
yes, ma'am. Yeah,
Yeah.
100.
So what you are saying here, the multiplication in the sync domain, you are just multiply it with the bandwidth by n times, right? And in the practice, you don't have this rectangular pulse. Instead, you will have the raised cosine pulse. And this function, this sync pulse is called a raised cosine. And instead of pulse, we take this as a raised cosine because the maximum information contained here at the DC frequency, which is at the lower baseband frequency, whereas with the time we require repeaters to boost the information, and if we have this type of information, then you will not have this 100, and you will have a far greater than bandwidth. I'll give you this homework to you. Similarly, find pulse n 100t frequency fs. We have found this sync n 100t as 100n. So what should be the pulse n? I should use a uh, thinner pen. So wait, what is my motto? I just tell you. So we saw sync 100t will have the fss 100, right? Then sync square 100t will have fs as 200. Similarly, we conclude here sync n 100t fs as 100n. You will have, definitely have. Then I'm asking, this is forming as raised cosine pulse. Here, this one. Although this has the bandwidth as infinity, right? It is taking up to infinity, but still we consider this pulse. And then pulse pulse 100t, you will have fs of what? Then pulse square 100t, you will have fs of what? Similarly, pulse n 100t, you will have fs of what? And here the bandwidth is limited. You have to make sure this is a bandwidth is limited. This is a t. So why we consider raised cosine pulse? And here the answer lies here. So this one is the homework for you, and I just want you to find out. And yeah, so in the future we follow it as a raised cosine pulse instead of this pulse function. Raised cosine
Ma'am,
pulse.
this one is the pulse, right? This of bandwidth T.
What?
This is the pulse for which we have to find this expression, right? This is time domain expression of the pulse.
Yeah, this is the time domain expression. You have to find the frequency domain of s.
Okay, ma'am, got it. Got it.
Yeah, you have to find this one. So yeah, I just want you to give some time, think, and then answer. So wait. Yeah. So if you know how the pulse sync looks like and how they differ, and how their sampling frequency varies, when the sync function is required and when the pulse function is required, you have achieved a greater level of understanding. And since you are also going to give some interview exams, so you will have definitely this type of questions, because this type of questions also asked to me. So I just want you to please look at it. Now, this, if you shift the pulse function by any time period, then you will have the shifting in by e power minus j 2 pi f t by 2, since you will have the Fourier transform, the mathematics, you know this, right? Then, similarly, the spectrum of pulse looks like here. Now, why this e power minus j pi ft comes? So here this term only makes difference in phase, whereas there is no difference in magnitude spectra. So in Fourier transform, we have seen You will have a magnitude spectra and phase spectra. So in the magnitude spectra, you might have seen this one is a even in nature, whereas phase spectra is odd in nature. For example, let's see e power e power at 1 upon a plus a minus a plus j omega e power minus at. This one is a Fourier transform, right? So if you draw the Fourier this the spectra, magnitude spectra, what is the magnitude spectra? If it is a f of omega, then what is will be the f of mod of f of omega? So what should be the mod of f of omega? It should
Ma'am,
be
1 by a at omega equal to 0.
a square plus omega square, right? And
Yes, ma'am.
sin omega square is equals to 1 upon a square plus omega square, right? Yeah. So you will have this type of spectra, f of omega and omega. What type of spectra you will have? Just let me know.
Ma'am, like you said, raised cosine, I think that only. 1 by
Yeah.
a 1 by a at omega equal to 0, and it will tend to 0 at the infinity frequencies.
So it will look like this one, right?
Yes, ma'am. Yes, ma'am.
Yeah. So this one is the even nature because here it is mirror with respect to y-axis, right? So this is mirror in respect to y-axis. So any Fourier transform magnitude spectra, if you draw, you will find like this only. And why this is required? Have you seen the Fourier transform property? Like I have asked you to see the Fourier transform properties of even, odd, imaginary, and real. Like Fourier transform of even signal is always real in nature. Fourier transform of imaginary is always odd in nature, right? So you have to see because I am why I'm saying I'll just tell you later. Now first let phase spectra or the Fourier transform. What should be the phase spectra? Let me know. F omega is this one. What should be the phase spectra?
Minus tan inverse omega by a.
Nice. Minus tan minus omega by a. Why minus? Because here is the denominator, and it will have the corresponding positive, which will be in the first, second, third, and the fourth. So here you will have positive, then definitely not directly tan inverse omega by a. Here you will have pi minus tan inverse omega by a. Here we'll have minus tan inverse omega by a, and
Ma'am,
here
I
we'll
think it
have
will be minus pi plus tan inverse
minus pi
omega by
plus tan inverse omega by a. Yeah, yeah.
no, ma'am. No, ma'am. I think third and fourth quadrant are interchanged here. They will be complex conjugate of each other. First and fourth, second and
First
third.
and fourth. Here it should be like this only. Second quadrant
Second
I
is
think.
also okay, ma'am. Third and fourth should be interchanged.
Oh yeah. I forget. Yeah, it should be negative, directly negative, and minus pi plus omega by. Yeah, nice. You had a good preparation. Okay, then here, if you just draw this, how the tan inverse look like? How the tan inverse looks like?
Tan inverse, ma'am, I don't remember, but we can try it at omega equal to 0. It will be 0. Yes,
Yeah,
ma'am.
it should look like this.
Pi, pi, periodic with pi.
Yeah, pi. But what I'm trying to say, at odd function, the magnitude at zero, it should be zero. First of all, you want to check like this. The magnitude of odd function f of omega at 0 should be 0. Then you have to see the symmetry with respect to origin. And you have find this is symmetry with respect to origin. And this one is this. Okay. So this is the properties of the magnitude and phase spectra. So the properties of magnitude and phase spectra is utilized for in the spectrum analyzer. So how it is utilized? For example, if you want to see you will definitely just see the magnitude spectra. If you want to analyze a phase, then you have to first check whether the function is having the correct Fourier transform or not. First, you have to check these two properties, like the even and odd properties, and then you say this, yeah, this function is having proper spectrum analyze using spectrum analyze. Have you ever used network spectrum analyzer in the lab or not?
No, ma'am, I don't remember using.
Okay, okay. Yeah, I think yeah, in BTech third year or fourth year, yeah, we asked you to use. So when the spectrum analyzer was given to us, so then we didn't realize the properties of this one. But yeah, we have to see. Similarly, for every modulation scheme like PAM, PWM. Later we will have PWM also, and P. What was other one? PWM, pulse width modulation, pulse amplitude modulation, and last one.
PCM.
P pulse, no, 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 PWM, PAM, and last one was pulse with the pulse amplitude, and
Duration
um,
with
I also I'm not also able to remember, but yeah, these amplitude modulations we have to check whether these are following or not. So similarly, when we multiply with the impulse train, then we are not getting these properties. Okay. So what is the another thing? So we are multiplying with the pulse train in order to get these properties of the spectrum analyzer or the Fourier transform properties, so that we will have the inclination with all the things. So in digital modulation, the basic difference between the digital and analog modulation is in the analog modulation you will have some boxes. Some boxes means uh, um, some circuits which are not required for other things. But in digital modulation, the same encoder circuit, the same decoder circuit, and the same demodulation circuit can be utilized for all the modulation schemes. So these are the properties of digital modulation. Beyond that, so the quantizer is also used. So the quantizer, we don't require different quantizer for all the modulation schemes. But same modulation scheme can be utilized. But here in analog modulation will have the frequency modulation, the amplitude modulation, the phase modulation. You will have a different modulation, different boxes, because we saw square law modulator, then we saw envelope detector, and then saw super heterodyne receiver in the future classes. But the super heterodyne receiver for the AM and FM should be different. So here there's a difference. So you have to remember this. So why pulse modulation that we have multiplied with the pulse train? So I have explained. You can just try to remember this. See how it looks like. This magnitude spectra. This one is the even function, right?
yes, ma'am.
Yeah. And similarly, if you draw the uh, phase diagram as well, you will have odd function. So sometimes we have to visualize the things, how the things are different, and why this one comes and why this was not sufficient, and what is the characterization of frequency domain, why we need only frequency domain transformation. So answer is not only we require to calculate the bandwidth. Since the bandwidth, we have very limited bandwidth, everybody is just running about it. We for example, millimeter hertz, which is a 60 gigahertz up to greater than 59 gigahertz, is yet to be standardized here in India, and we are running about it because it is a very precious quantity for the communication purpose. So you have a think about it like 6G. Why 6G has not come? Because this is the reason, because the frequency is very limited, and we have to standardize it before using it. So frequency domain is required to analyze the signals and to analyze the system. And through the Fourier transform is a greater tool to understand the frequency domain signal, because without it we cannot transform, we cannot see it. And beyond it, we also have jet transform, we also have Laplace transform, and Yeah, these three transform we have. So what is the difference between these threes and where it is required? Um, KG Krishna sir, you have done the course of digital modulation and signals and system you are also doing. Can you please answer, or I want to know, like,
Uh, me, madam, myself.
yeah, I'm just asking to make the class interactive.
Okay.
Yeah, yeah.
Okay.
Mm.
I'll explain as I understand.
Yeah, yeah.
See, Fourier transform basically, gives a frequency representation of the signal in the time domain.
Yeah.
Okay. So,
In the frequency domain.
yeah, it says what frequencies are present in the time domain signal. Okay.
Okay.
Uh, say Laplace transform is actually generalization of frequency transform, wherein we introduce the term not just j omega, but sigma plus j omega. Okay.
Yes.
So basically, Laplace transform is a mathematical technique. For any kind of signal, we can have a Laplace transform, but frequency transform is only for converging for a period for a for a finite uh, a periodic signal. Okay.
You
It
said
should
this
be a
is
stable,
only
ma'am,
for.
right?
Yeah, yeah.
Okay. So, because how I visualize this, that S is sigma plus j omega e to the power of minus st. So, what Laplace transform does is it makes the signal decay or converge to force it down so that we can have a transform. Any signal can apply to Laplace transform. Okay. And when sigma is equal to 0, then it becomes a Fourier transform. Okay. So,
Okay.
and the Z transform is actually a discrete equivalent of Laplace transform, where instead of S, we have a Z, which is R e to the power of j omega. Okay. So there we assume for normal DFT, we assume R equal to 1. Just like in Laplace transform, we say sigma is 0. Uh, in Z transform, we assume the magnitude of Z is 1, and so it is a digital equivalent of
Sir,
Laplace.
in jet transform also we have you remember are you remembering this ROC term? So what is the significance of
Yeah, yeah.
ROC?
See, yeah, whether a Laplace transform or a Z transform, ROC indicates uh, where for which values of S or Z uh, the Laplace or Z transform exists, a transfer function exists, converges. Okay,
Okay.
converges. So, in case of Laplace transform, for it to be converging, it should
Okay.
be on the right hand side of the S plane. Okay, so
Okay.
suppose there are poles in the Laplace transform, and uh, yeah, I don't remember, but it is something like right hand side of S plane. It says it is stable. Stable means converging. Yes.
Okay, sir. So you are saying that Laplace transform and jet transform, can we say like Laplace transform, jet transforms are used for the analysis of system, LTI system?
Yes. They're used for systems only. For example, transfer function. System is characterized by a transfer function, h
Yeah.
of z. In case of Laplace transform, h of s.
Yes.
Okay.
So
So,
transfer function is also defined for only those who don't have initial condition. For example, if we have initial condition, the Laplace transform and jet transform fails. Like really, Re right?
yeah,
We
yeah.
cannot use the transfer function term here because y is divided by xs provided only when we have the initial condition as 0. So
Oh,
what we do usually when we have initial condition, how to analyze that systems who have initial conditions.
okay.
So
So,
that is I want to answer, I want to know. Sir, literally I really appreciate you, like you are from mechanical
yeah,
background, but
yeah.
still you do have understanding of this jet
Let
and
me
Laplace. Yeah.
let me understand. If we have initial conditions, It is bilinear. It is uh, it is see, Laplace transform we consider only one sided, but if it is sorry, I'm just little vagueness. So madam, there's one more thing which I getting confused in the communication terminology is
Yeah.
baseband, narrowband, and broadband. See, I
Okay.
tell you what I understood, and you and I tell you where I get confused. See,
Okay.
broadly I understand normally when you say bandwidth. Bandwidth means the highest frequency minus the lowest frequency contained in the signal, right?
So you can say the range of frequency, the range of positive frequency for which the amplitude is constant. That,
Ah,
huh.
yeah, the range of positive frequency. Okay,
Hmm. Hmm.
positive frequency. Range of frequencies contained in the signal is called a bandwidth.
Yeah.
And narrow band means the the range is smaller.
Yes, the range is smaller, and the one more thing I'll just ask, think about it. Like after before modulation, whether you have narrowband signal, or after modulation, whether you have wideband signal.
That I can answer. See, before modulation certainly is a narrow band.
Okay.
See, after modulation, because modulation is done by carrier makes it broadband. Carrier increases the bandwidth, right, to megahertz, from kilohertz to megahertz. It transfers
Uh,
by
so
so
you
after carrier, it becomes actually broadband. That's what I understand.
so
Before modulation, the signal is a narrow band. That's what my interpretation.
so the narrow band. Okay, okay, okay. I'll just tell you this one. Yeah. So people have this misunderstanding that after modulation you will have the broadband. But no, after modulation you will have definitely the baseband to band pass modulation, but you will have a narrow band signal. Why?
Oh,
I'll tell you. So I also had this confusion there when I studied this. And so then I did find what is the scenario, actual scenario. So here, what is happening in before modulation? Yeah, here I'll also ask questions from other participants about these things so that I just want to know where the thing you don't know about it, where frequency transform is required and all. Before that, we'll answer this question. Before modulation and then after modulation. Yeah. So before modulation, if you say this one is MF and this F, what is that? It is a shifted version of FC, then FC plus W and FC minus W, and then is minus FC, minus FC plus W, minus FC minus W. This one is this one is 2. Yeah. So yeah, this one is a base band and this one is a band pass. Definitely band pass because here we are shifting it to a higher frequency. Now just think about it. Like why it is narrow band and why it is wide band. I'm saying, and this is true. This one is wide band.
okay. One
This
more
one is
thing. One
narrow
more
band.
clarification about the term. Baseband means the native frequencies in the original message. That's called baseband, right? The
Negative.
word baseband,
Mm-hmm.
normally we use it for the frequencies range in the original MT.
Okay.
Is a baseband. For example, the human speech.
Mm-hmm.
What is the baseband frequency? When you say baseband means 4 kilohertz.
3.5 kilohertz we have voice frequency, right?
Yes, that
Hmm.
we call 3.5 kilohertz is a baseband frequency.
Yeah. This one is wide band. I'm answering you answering this.
Oh, yeah, yeah.
Just this
Again,
is
we
narrow
brought
band.
a wide band, broadband, baseband, narrow band.
Okay. So this one is band pass and this one is base band and this one is wide band chord and this one is narrow band. Why this is. So, Kushid, can you think something like why this is wide band, that's why this narrow band?
No, ma'am. Actually, I associated these terms only with FM. Like we have a narrow band and wide band in FM. In wide band FM, it extends to infinity.
Yeah. I just
That's
I
the
wanted to
concept.
come into that. So, sir, in modulation techniques, we saw after modulation, we are assuming the 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 frequency narrowband frequency modulation and wideband frequency modulation. But in practice, we generally have beta less than equals to one. That which is a case of narrowband.
Ma'am,
So,
actually, I have one more doubt here
uh,
that why we are applying this wideband and narrowband concept here. The bandwidth of this signal is actually same. This shifted signal also it is actually two times FM, or in case of SSB it will be simply FM, and here also it is simply FM. So why we are considering it wideband? This is as narrowband.
no. Wideband, narrowband, the term it is there, and the technologies applies to that. So term
Okay.
why it is called wideband and why it is called narrowband. Yeah, you are right. Like why we are taking here just is the bandwidth here is 2 YW and
Mhm.
here bandwidth is 2W.
Yes, ma'am.
Yes. So why modulation is required, you know the concept, why it is required. But
So
why
this
this is
term,
called
ma'am, this term wideband narrowband has nothing to do with bandwidth of the signal.
no,
This is
no,
something
no,
else.
no, no, no. Yeah. So,
Okay.
I'll tell you, the modulation is a process of converting a wide band and baseband signal to a band pass and narrow band signal. So we are converting this one. Why this is? So you can see what is the maximum frequency here. Maximum frequency. The maximum frequency is W. What is the minimum frequency here? Zero, right? So if you take this max f and min f division, you will have w by 0, which is infinity. Now if you take min f, which is fc minus w, and max f, which is fc plus w, if you take the division fc plus w, fc minus w, it will converge to some point, right? It will have some value because w is far less than fc. You will have some values which is nearer to 1 or greater than 1.5 or like that. I remember this question because we had in gate exam. So yeah, this type of the concept is there. So here the variation from a minimum frequency to maximum frequency is ranging to infinity, which is a baseband signal, and we are converting to a narrowband signal to this point. So this is why this is called narrowband. This is why this is called wideband. So this is the
Okay,
answer.
ma'am, this is clear. Ma'am, one more question. Kindly clarify this term baseband also. What exactly it means?
So baseband. So baseband मतलब means base होना चाहिए. You remember हिंदी, you know हिंदी ना? तो
Yes,
base
ma'am. Yes,
होना
ma'am.
चाहिए. तो base कहाँ है? Even the zero frequency क्या होता है? Zero frequency is DC frequency. So
Ma'am,
DC frequency it has
okay,
association
ma'am.
with that. Otherwise we are shifting it to a higher frequency which is FC. FC is far higher than that. FM, which is 3.5 kilohertz. In AM modulation, what is FC? FC is 1000 kilohertz, and 1000
Mhm.
kilo is far greater than 3.5 kilohertz.
Okay, ma'am. Ma'am, in the case of voice signal, its frequency range is suppose 300 to
3.1.
3.1 kilohertz, right?
Huh.
So if we are getting voice signal in this, then we will call it the baseband,
Yeah,
right? Okay, ma'am.
yeah. After modulation, whatever signal you will receive, you will have band pass.
Okay, ma'am. Got it.
Yeah. Sir, did you what?
Yes, madam. You made one statement. Can you repeat? Modulation is a process of converting wideband signal to narrowband signal
Yes.
and baseband signal to band pass signal.
Yes.
Okay.
Yeah,
So,
huh,
yeah, modulation converts wideband to narrowband. I thought it's a reverse. Okay.
yeah.
Wideband to narrowband. Okay. Baseband to band pass. Okay.
So
Okay.
whenever you'll have this type of terms, you just try to visualize it with this modulation process. You will definitely get that point.
Okay. Okay.
Okay, so we will come back to this point. So you were you were answering that question. Can you please continue or I want to know more about Fourier transform and comparison between Fourier transform and jet transform and Laplace transform.
See, Fourier. Okay, okay, but we understand, right? Laplace transform is a generalization of a Fourier transform, wherein if you put sigma is equal to 0, it becomes a Fourier transform. Okay.
Wait, yeah,
So
huh.
Z transform is same as Laplace, except for it's a continuous. Sorry, for discrete type. Instead of S, we use Z. Instead of S plus j omega, we use R e to the power of j omega. Okay. So conceptually both are same. Laplace and Z transform are same, except the mappings when it comes to the convergence ROC. In case of Laplace, it is something related to left hand side and right hand side of S plane or something. In case of Z transform, it is a unit circle. Inside the unit circle or outside or unit circle contained in ROC. That kind of criteria. So, but conceptually, both are same. Both are same. One is continuous domain, other one is discrete domain.
Okay, nice interpretation, and I'm very glad that you know. But you one statement question, can you tell? Like I also want to know from you.
What, ma'am?
Difference between all
Okay,
these
ma'am.
things.
These are, ma'am, different transform. Frequency transform is only suitable for the stable. Only stable functions can have this Fourier transform. And
Stable.
Laplace transform, J transform, they are generalized cases. And if we are thinking of relating them, then unit circle in the J transform. This imaginary axis in the Laplace transform corresponds to this frequency Fourier.
You said one statement Fourier transform is only applicable for stable function.
Yes, ma'am. Where this j omega axis should lie in the region of convergence in terms of Laplace transform for those signals only, or we can say that the impulse response is absolutely integrable. Only those functions can have this Fourier transform.
Okay.
Madam, it is true. Fourier transform is applicable only to finite energy signals, which is stable, right?
Yeah, this one only I am trying to get the answer from you. Dirichlet condition.
Yeah, Dirichlet conditions,
Huh.
finite energy and finite number of peaks, finite number of
Continuities.
discontinuities.
Yeah, yeah, yeah.
Yeah.
This is all about the Fourier transform, which is only applicable for a stable function, and the finite signals, and which have finite energy and finite number of discontinuities, and finite number of maxima and minimas also. Okay, so the Fourier transform is applicable for that, but the jet and the Laplace transform are actually for the analysis of also for the unstable system we have in practice, to determine the stability, to determine the linearity, to determine the superposition principle, and to determine all those properties of the system. So yeah, jet transform and Laplace transform. So one thing, the 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 addition of sigma, which is very important. Why it is required sigma, why not only j omega, is a big question. Like why sigma is required, there's a good answer about it, like why we know do not
Yeah,
yeah.
yeah, madam, I have already shared that without sigma makes it stable, makes it finite energy signal because, for example, if it exponentially growing signal is there, there is no way we can have a Laplace transform for that. So, sorry, there's no way we can have Fourier transform for that. But we can
Yes.
have a Laplace transform because the sigma minus sigma st, which is pushes it down so that we can have at least Laplace transform, if not a Fourier transform. Right.
Yeah, yeah, yeah. So, right, sigma is required for that to make it to have the converging response
Yeah,
at the
convex.
end. And the jet transform is just a discrete form of it, and we also call DTFT if R is equals to 1.
Yes,
So,
yes.
these are all the transform in the frequency domain. So, here all these transform are in the frequency domain, whereas this one is only in time domain.
Yeah. Yes, because Fourier transform conceptually breaks the signal into a series of harmonics, combinations of harmonics. Actually speaking, I don't know, madam, but I still call it is a transformation. Only thing it's a line spectra. At the Fourier series is nothing but if you represent it as a spectrum, it is a series of lines on a frequency axis.
Yeah, but this there is a limitation like Fourier series is only defined for periodic signals. Periodic signal it is only defined for periodic, whereas all these signals are defined for all signal irrespective of the fact whether they are periodic or not. So Fourier
Yes,
series, first we are seeing that whether it is periodic or not. If it is periodic, then we are writing in terms of harmonics of sine and cosine. So we are breaking it down to see visualize it more clearly, and we will have some properties of that. So Fourier series is not a transform; it's just a representation in the time domain itself. So it's like that I'll say. But yeah, if you are seeing like it's a transform. If it is a transform, then it should have some effect in the spectra. Like, yeah, spectra. We for the better analysis of spectra, we do Fourier series thing.
yes, yes, I agree with madam. It is not a transformation. It is a series expanding a periodic signal into a combination of a harmonic signals, sinusoidal signals. But if you plot it on a frequency axis,
Yes, yes,
you get a line spectra, right? Which is not periodic. Actually, you take a periodic signal, Fourier
yeah.
series periodic signal, in a quote unquote frequency domain. If you say actually it is it periodic or, or a periodic?
Sir, can I know what is the spectra? Yeah, think about it. The spectra of the pulse
Huh?
train spectra.
Yes. So if the input is a pulse train in
Hmm.
time domain, in frequency domain, it is periodic of sync pulses.
Yeah, the sync is not periodic.
Okay, okay,
Sync,
okay.
huh.
Then what will be in the frequency domain?
No, no, no. It is not like that. Yeah, it's sure that if the input is periodic, it's not necessary that it will have periodic. But yeah, the sync function, the shifted sync function. Kushid, you also saw like that in previous class. You told me the expression for the pulse sampling, right? That you have got the if, sync shifted response. So that is
Mhm,
not
yeah.
periodic. So it is the odd function.
Ma'am, actually, I have to say something regarding this Fourier series. Yes, it is not a transform in the sense that it does not affect the frequency spectra, but it helps us in easily getting the frequency spectra of the periodic signal because its Fourier series coefficients, the Fourier transform of the periodic signal is simply its Fourier series coefficient shifted by those harmonically related impulse, whatever that harmonically related frequencies are there. So
Yes,
it
yes.
helps us in getting it simply Fourier transform. We can simply get of a periodic signal by converting its form into Fourier series in the time domain.
Yes, yes, yes. So this is all about the spectra and all. So I think if you go to the discrete, like sir, you have done that course of this digital modulation, DTFT, DFT, and FFT, and the continuous time periodic. I draw the table of if you have input of continuous and periodic, then we'll have to have continuous and periodic. So that the understanding should be there while analyzing the system. So I'll just say to please saw that. As I think 1 hour left, so we will solve the questions. So this is all about the equalization. So equalization is nothing but a filter. We are passing it to a filter, and that filter itself will have the sync type of function. Yeah, see, we can see the filter bandwidth should be fs by 2. Uh, think, yeah, I think this one is 1 by PF equalizer. So yeah, I think you have read this now. So why this? What is windowing? Can somebody tell me? So were saying about the filter design. So in that we use the term of windowing.
Madam, I heard it, but frankly, I have not understood. Okay, so I may have to read once again.
Okay, okay, no issue. Question, you have read this module, right?
Yes, ma'am. Just one second, ma'am.
Yes.
Reverse distortion caused by windowing with sync function. Ma'am, I think sir is referring to the distortion caused when we were interpolating with sync function.
Okay,
And
that
sir
is
is
that is nice,
simply,
but yeah, windowing itself has some significance.
I don't recall, ma'am.
Butterworth filter, Chebyshev filter, in that also we refer to windowing. Filter design, we will have the filter coefficients like when we design a filter, like when we have sample and whole circuit, we get the samples at every ts. Similarly, when we design a filter, we have to get the filter coefficients, and how many filter coefficients are required, that is defined by windowing technique. So we'll have the windowing technique as well in the filter design. So it's okay if sir has, I think sir has not covered that too, but it's okay. Uniform quantizer, Mildred quantizer. So this is all. Sir, you have read this all in digital communication, right? Quantization.
Yeah, yes, madam. Broadly, I understood, but not very
Okay,
detailed.
uniform quantization, delta ratios. Okay. So yeah, we'll move to the questions. We have to take questions at least of 10 with instruction given by them. So yeah, we'll solve the questions.
Madam, just one more general question,
Yeah, yeah.
conclusion. Generally, that transfer function, the word transfer function means describes only LT, it is systems, right? LTA system,
Yeah,
H of
yeah.
Z or H of S or H of N. Okay, it's
Yes.
only it is only LTA systems, and signals won't have transfer function. Signals are signals.
Yes,
Um,
yes.
yes, signals can have a Fourier transforms. Signals can have Laplace transforms. Signals can be represented using Z transform. Correct?
Yes, yes.
Yeah.
Mm.
But transfer function, the word means it is a system.
It's a system. Yeah, the signals and system just get differ only by this transfer function. The
Yeah,
term.
but yeah, exactly. Because where I'm getting confused is normally any expression in the Z's and S's, until unless someone tells me whether it represents yeah, if it is a numerator denominator, I can easily make out it is a transfer function of a system. But if it is simply one numerator, an expression, polynomial,
Expression. Yeah, yeah, yeah. Hmm.
yeah, I get confused without because just a polynomial can also represent a system, no?
It can also represent a system. It can also represent signal.
Signal.
Hmm.
Yes, yes, yeah, yeah. So just by looking at it, we cannot make out. We have to say clearly it is system or a signal. Okay, okay, right.
Okay, one more question I have for you. Like for every transform, we saw that we have to analyze the system. In using Fourier transform, we can also analyze a stable system. If we are using Laplace and Z transform, also we can analyze a system. But yeah, for the system to be analyzed, we require the initial condition to be zero. Why? Why it is required? And what happened if we don't take the initial condition to be zero? And what will be the transfer function for this? But yeah, the transfer function cannot be defined for that. I'm answering that question. But yeah, why it is not defined? And what to do with that type of system with some initial condition? Because there can be some initial condition system, right? It can have
Uh,
some initial conditions.
no, no. If it has, see, if initial conditions are zero, we understood. We can imagine all the systems have initial condition zero or stable. We can do. If initial conditions are not zero, then I don't know. Maybe they are not stable.
No, that is fine, sir. but there are systems, right? In control theory, will have some systems which have some initial condition not equal to zero. In analog circuits also will have. Yeah, yeah, Kurshid.
Ma'am, in such given systems, what we will do, we can't go by transfer function approach, but we can get some relation between input and output by using that transfer function, and then we will go for this.
No, we cannot say that
Okay, ma'am.
yt is equals to ht convolution with xt. We cannot
Yes.
say ys is equals to hs into xs. So how we will
That
answer?
is yes, yes, ma'am. That is not possible. I'm coming to that, ma'am. Actually, from theoretical perspective, I'm coming to that.
Okay, okay. Yeah, yeah.
Suppose we will get this transfer function expression, assuming that initial condition is zero. We will ys and xs. We will write it simply in the Laplace domain concept, and then we will use these properties of Laplace because it accounts for the initial conditions, say differentiation. So there we will put the expression for that initial condition, and then we will get a different sort of expression. One will be this input multiplied by that transfer function term, and one will be extra term. That extra term will account for those initial conditions. So
Okay.
mathematically we can proceed for that.
What? Can you repeat? We didn't get this.
Okay, ma'am. First of all, we will assume that initial condition is zero for the system,
Okay, first
and
we will. Acha, acha, acha. So have you heard about differential?
yes, ma'am, that approach actually I find it quite difficult and boring also. So I go from this approach using Laplace domain property.
Okay,
That
okay,
is actually quite boring, ma'am. That is
okay,
approach is also good. By the-
okay. So will solve it into using differential equations.
Okay,
And
ma'am.
generally, but yeah, I have not solved using your approach. Like first we will assume initial condition to be zero. Yeah, that was also like first we have to modify. We have to write the system equation in terms of differential equations only. Then we have to take the
Yes.
Laplace transform, and then assuming
Yes,
what you
ma'am.
are
Yes.
saying, we have to solve.
Adam, in mathematics, they call something like a steady state response,
Yes.
assuming initial conditions are zero.
Hmm.
Maybe, and
Yes.
then transient response, steady
Yes.
state response plus transient response.
Other name is there, I think. Steady state response is fine, and CF and CF, what is that? I am not remembering. Yeah, but we have to bifurcate it. Like first we have to assume as an initial condition zero, then we have to take that as an input, and then we have to solve. So like yeah, steady state response and transient response. Some other names are also exist for these two responses. So we have to bifurcate it and we have to see. So that is a model using differential equations. So that is also important thing, like how we will solve. So that there the transform function doesn't exist. And yes, sir, you were saying something.
No, madam. No, madam. I'm just thinking. Yeah.
Okay, okay.
Ma'am, that is particular integral and something we call PI and
cf CF and pi, right?
yeah, complementary.
Complementary function and
Yes,
pi,
ma'am.
yeah, CF and pi, we solved it that using that. So that is also first we have to model using differential equation, then only we'll solve. First you'll, yeah, you're saying good, that we'll first assume initial condition to be zero, then we'll assume input. So that also we have to model using differential equations. Mm. So yes,
Madam,
mm,
one more general conceptual question.
mm,
System, suppose filter is a system, right?
yes,
Modulator,
is also a system.
an LTA system?
It's a
No,
system.
not LTA system.
No, modulation. Wait a second.
Modulation
Modulation.
changes frequency, right?
Yes, so why not it is LTI system? It will be LTI. See, I'll just tell you using this.
Take any modulation, AM or FM,
See, this one,
modulate.
yeah, I am taking using this amplitude modulation. So I will try, I'll just say, just remember this. If you have input like this, A sine omega t, and if you have input as A dash sine omega t plus phi, you will have LTI system. And in amplitude modulation,
Yeah,
AC.
amplitude modulation is an LTI. I can understand because frequency doesn't change, only amplitude changes.
Yes, 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 yes.
But FM modulation
FM also we will have only shift in this one.
shifted only.
Yeah, but sinusoidal nature will have now, because input you have sinusoidal and output will also have sinusoidal. This can change. Phase and amplitude can change.
Okay. Okay.
This frequency will remain same. That coming from the input side, that frequency will remain same in FM also.
Phase. So FM you are saying FM. Wait a second. FM what we have? FC plus del F. FC minus del F. So yes, 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 you are right, sir. FM will not. Yeah, frequency should be same. Phase will be different. So phase modulation is a LTIE, but a frequency modulation is not an LTIE.
Yes, I need clarity. So this question. Yeah. So, so I was telling to some other my general audience. You said that whole DSP is all about systems, and the systems, any system, whether a digital system or nothing but modulators, amplifiers, filters, etc., all can be represented by transfer function. That's what I'm making a general statement. So I
Yes,
want to
yes,
validate
yes.
that. That's it.
Okay, nice, nice, nice. Thank you. But yeah, the frequency should be same, like sine omega t, sine omega t. Sinusoidal nature should be same, like sine and cosine are also sinusoidal. The phase and amplitude could change. So yeah. So let us solve this question quickly. Consider the signal MT that is band limited to frequency FM. Uh, so I just want to know, like, whatever the questions I discussed here might be the same question for you, or might be different, because I'm discussing the questions which has come in the previous course. So yeah, you can grab some understanding, though you have done your assignments. But yeah, because we have to go using through using the specified instructions. So I cannot jump for the week 8 right now. But yeah, in the last 2-3 weeks, I'll definitely solve some questions related to your questions, so we will have the better understanding. So for now, let's do this. So the consider the signal empty that is banded to FM, the minimum sampling frequency, which is to avoid the spectral distortion.
Is it 2 FM?
Yes, yes, nice.
2 FM.
Yeah.
Because
Yeah, we
this
will
is a
solve these questions quickly, which are easy. Consider the signal empty. What is the minimum sampling frequency required for no distortion?
And
so
100
it's
hertz.
100.
Why it is 100? Because
Because 2 pi ft, 2 pi ft, so f is 50 hertz, so double the frequency.
yes, yes. Here, what will the amplitude? 1 by 2, right? So this one is bandwidth. Positive frequency, we only consider bandwidth. And then Fs is equals to 2 into Ft is 100. Nice. Now, I'll ask a good question. What is the bandwidth for cos 500t pi t plus sine 600 pi t plus sine 700 pi t plus cos 800 pi t? Yeah.
So madam, I tell you what I'm going to do. I
And
find out the highest frequency in all the sinusoids. Cos, for example, the highest is
and
uh,
400.
in the cos 800 400. So the uh, yeah, 400 is highest. Lowest is 250.
Yeah.
So 500 minus 250. That is the bandwidth. No, I don't know.
Uh, I think, sir, the bandwidth, first we have to make the spectra, right?
Yes, yes.
Spectra, let's make it. What is the spectra of this? This will have 250, 250, then 1 by 2, 1 by 2. Sine will have 1 by 2, minus 1 by 2,
Madam,
plus 1 by
this
2.
negative only always me fearful of me.
No issue. You will
No,
only
no,
face difficulty in summation of negative frequency when you have. We'll
no,
solve
no,
some questions related to that.
no, no. When you say bandwidth is a difference between maximum and minimum minus FM to plus M, the difference between minus FM to plus M is 2 FM.
Yeah, no, no, no. That should come into positive frequency. Then only bandwidth is defined.
Oh, we have to always take only positive side and then compute bandwidth.
Yeah, only positive side. Then we have to compute the bandwidth. And one more thing, the Nyquist rate is not defined for the Fs is equals to 2 into bandwidth. It is defined for 2 into maximum frequency. This one
Oh,
FM is the maximum frequency. It is not the bandwidth. FM is not the bandwidth here.
okay.
So in the spectra, we have to define, we have to see the maximum frequency. So what is the maximum frequency?
So maximum is 400.
Yeah. So 400, the Fs should be 800. Simply it will be 800.
Yes.
So I'll just draw the complete the spectra, 350, and then cos is there, then 400, 400. Yeah,
Okay.
so this is
Okay.
the spectra.
Okay. Okay. For drawing the spectra, since cos is an even function, you are putting everything in the positive side. For sine, you are putting in the negative direction, right?
Yes, yes, yes.
Okay. Okay.
Why negative? Because here you will have e power minus j 700 pi t plus e power plus j 700 pi t divide by 2, and in the frequency domain it should be the shift in what, oh, f
Shifted
minus,
impulses.
yeah, and minus should be there because here
No,
negative negative and positive, minus divided by 2 plus del f plus 100.
And it should be 2j, right,
2j,
in
ma'am.
the
2j,
sign.
2j,
Yeah, yeah,
2j.
yeah, 2j, 2j. And here it should be only magnitude spectra is there, then magnitude should be there. Then yeah, if you draw this, here you get. With J, we don't consider this is a magnitude spectra, right? So whatever the spectra we draw here as magnitude spectra, the magnitude of J is 1, right?
Okay, ma'am.
Hmm. So you will have the this one Fs is equals to 800. So I think you will not have any issue in solving these type of questions. Now let's solve this question. Yeah, this question I want you to solve. This question, if you have able to solve, you can solve any question related to filter and passing through filter and getting what frequencies. So I'll try it. I'll just read this question. Consider the sinusoidal signal MT is equals to cos 2000 pi t. It is sampled using an impulse train with a sampling frequency Fs is equals to 1.8 kilohertz, followed by a low pass filtering with an ideal low pass filter of cutoff frequency 2 kilohertz. What are the frequency of the sinusoid present in the resulting signal?
Ma'am, C 1000 and 0.8 kilohertz only.
Okay, okay, okay. Let's see what is answer. Sir, you also please solve.
Madam, so here only I get confused about the notation. I tell
Yes,
you
yes.
that the sinusoidal message signal is 1000 or 1 kilohertz.
Okay.
So
So whenever
FM,
we'll have this type of question, we'll draw the spectra.
yeah.
Okay.
So FM is 1 kilohertz, and FS is 1.8 kilohertz, and this filter does with a cutoff. That means it allows all the frequencies up to 2 kilohertz. That means one, I don't know. This out
Okay.
I am interpreting my understanding. So this filter should cut off beyond 2. Sorry, beyond 1.8. That means
Okay.
because I make an intuitive, so mathematically I get lost. It's
No issue, no issue. Because here, like Kurshid has solved correctly, I think. That is very good.
so yeah.
Yeah. So we'll see. Sir, this is after the sampling. Like after sampling, this is the MF, and after sampling, we'll get this expression. Okay. So
1 minute, madam.
yeah.
So after sampling, the frequencies contained are 1000. Okay, okay. Okay, this is before sampling, right?
Yeah,
MF.
this is after sampling the expression. Expression after sampling.
Okay, okay. But the spectrum you have drawn is
Yeah, before
before
sampling.
sampling. Yes.
So I'm trying to make after sampling spectra. So let us draw this MSF. So this 0 will come here Fs. Now Fs, what is Fs? 1.8. Here 1. So what should be this? 1 plus 1.8? 1 kilohertz. 2.8.
2.8.
Here 1 minus 1.8? 0.8 kilohertz.
One.
Definitely then Fs, like you will have these frequency. Wait, I'll show
Ma'am,
you.
there will be one unshifted spectra also.
Yeah. NFS F. So here, suppose this is 1 minus, if n is equals to 1, then 1 minus 1.8. Here minus zero point 0.8, right? So you will have minus zero point 0.8. Then if you have NFS, F minus NFS, 1
Ma'am,
minus,
if n is
yeah,
zero, then if n is zero, then there
yeah,
will
F,
be one between point
yeah,
0.8 and
F n is equals to 0, the 1, you will have also 1 kilohertz. Similarly, when you have n is equals to minus 1, what will have? Minus 1, then 2.8. 2.8. Similarly, we have to vary the n values. What could be the possible n values? Okay. And how you got zero point 0.8? Then I am not getting zero point 0.8. F.
ma'am, here it is point 0.8 when we will apply. You have drawn actually this first spectra at point 0.8 kilohertz.
No. So zero point
Yes,
0.8
ma'am.
means, so how we are getting zero point 0.8? F minus F is what? Acha, minus. Okay.
Fs
F F
minus F.
F F also is minus 1. Okay.
Yes, ma'am.
So minus 1 plus zero point 0.8 is zero point 0.8.
Yes,
Sir, are
ma'am.
you
Yes, ma'am.
getting what I'm doing? I'm shifting this MF to to this part. So we are varying this n to minus infinity to plus infinity so that we can have filter value of up to 2 kilohertz. So I'm not worrying about beyond 2 kilohertz. There will be some frequency here also. Here also. So what could be the filter values up to 2 kilohertz? So this one is 2 kilohertz. 2 kilohertz. Sorry, 2.8 is also beyond that. So 2 kilohertz.
Okay.
These
So
frequency will only pass.
zero point 0.8 and 1 kilohertz. Only those two.
Yeah. So you have to remember this time domain the time domain frequency domain representation of this sampling and sampled signal. Then you have to visualize it, like how we can draw, how we can see n is equals to minus infinity to infinity till up to low pass sampling frequency, which is 2 kilohertz. So answer is this one.
Yes.
Anyhow,
One.
we are not getting zero point 0.2. So by varying any value of minus infinity to infinity with f minus 1 or a plus 1, you will not get zero point 0.2. So yeah, this was also my expectation. This one we are getting 1 kilohertz and zero point 0.8 kilohertz. Did you got, sir?
Okay. So you only consider positive side.
Yeah, we have to only consider positive side in this type of questions. We cannot consider negative side. Negative frequency are never exist. So why we have considered minus here? Because we have the Fs is as plus. So 1.8 minus 1, which is making positive, which is important to us. So we are
Okay.
considering
Okay.
2 kilohertz. Okay. So let us solve this question. Consider the signal MT is equals to 20 sync 100 T. What is the minimum sampling rate required for the signal to avoid aliasing? A tau sync F tau will have,
Ma'am, 100. It's fs by 2 will be 50 hertz. So
Nice, nice. Hmm.
Okay, can you explain, madam? Minimum.
Sure, I'll explain. See, this is M, F. This is F, and this is M.
So, but the generally, okay, minimum sampling rate to avoid distortion is twice the maximum frequency. So,
Yes,
find the twice maximum frequency of the sync function.
yes, yes. So what I'm doing, this is a time domain. A is what? 20 here, and T is what? 100 pi T. So this MT is 20 sync in 100 T. Okay, 100 T. And what you will get in the frequency domain? This is frequency domain. You will have this one. 50 minus 50 and A is 20. Okay, so 100. So maximum frequency is 50.
50
FS
hertz.
will be 2 into 50, which is 100. So did you got?
Okay,
Yes.
okay, ma'am.
Yes. So sorry, answer will be this. So you have to remember this pi is not required. So you have to see whether here it is pi or not. If it is here, the pi is there along with sync, then here it should also the pi term should come. So you have to see. Now consider a message signal MT with a maximum frequency FM. The minimum sampling rate required to sample this signal to avoid distortion of the spectrum is termed as.
Nyquist rate.
Nyquist ray.
Yes.
That is.
So Nyquist. Now let us solve this question. Consider a signal MT with spectrum MF, which is sampled with an ideal impulse train of sampling frequency Fs. The spectra of the sample signal is.
And C.
I wrote this equation. Yeah. So you will have uh, this one as MF. You will have MSFS Fs summation of minus infinity to infinity F minus NFS. So we'll have this one, this one, this one, this one, this one, Fs Fs 0 minus Fs minus 2Fs. So answer will be C.
Madam, here we can also say that sampling is nothing but modulation with impulse train.
Yes, yes. That is what the PAM is.
Yeah,
Modulation with the pulse train.
yeah, modulation with pulse train.
Yeah.
So that's why we are multiplying by Fs
Mm.
in the frequency domain. Yes,
Yeah,
yes.
we are multiplying with the PT, which is a train, pulse train in the time domain, then we are getting this type of spectra in the frequency domain. Now, let us consider question number 7, which is consider the signal MT is equals to 10 sync FT. What is the same question? Huh? No, no, different question. What is the answer?
Almost the same question. 5. 5.
10, right?
Ma'am, it should be 5 na. 5.
Okay, yeah, yeah, yeah. 5. So FM should be 5. FS should be 2 into FM, which is 100. So the F,
Ma'am,
yes.
FM is
Ah,
2.5 actually. FS by 2.
2FM. 2 into 2.5, which is 5. Okay, okay. So you can see this the sampling frequency is irrespective of the fact amplitude, amplitude. In fact, summation also. Sampling frequency doesn't depend on summation also. So only we have to identify the maximum frequency and we have to multiply by 2 that to get the next figure. Now, this question. Consider the sinusoidal signal MT is equals to 600 pi t. It is sampled using an impulse train with a sampling frequency. Yeah, I want to solve. I want to get the answer. Similar question it is, but yeah, I want to get the answer.
Ma'am, B. B.
B.
200, 300 only.
So you have to see
And
first. Fm is equals to 600 and minus 300. Okay. Fs is equals to 500. What frequency we can have? Sorry, FFM minus plus NFS or minus NFS, where n is equals to minus infinity to infinity. Now, in order to get to 300, and what is the ideal low pass filter? 600. So FC is equals to 600 hertz. So in order to get a 300 n is equals to 0, you will have FM as 200 after LPF. Now n is equals to 1 if you say, what is that? 500 minus 300, which is 200. Okay.
200 and 800, ma'am. So 800 will filter out.
Okay. And another frequency, okay. Whether we are getting 100 or not,
No, ma'am,
we
I
will get
don't.
100. No, we won't get. We will get 100. 500, 1000 minus 700, 1000 plus 700. Okay, we will not get 100. Okay, then answer is this one.
Okay, 1 minute, madam.
Yes, yes.
Okay, to understand intuitively, okay, you uh, see, low pass cutoff frequency FC is 600, but you made as 300. No, yeah, FC is 600. When you say cutoff frequency is 600, that means all the frequencies, the signal should be less than 600. Okay, so less than 600 means that the maximum frequency plus something, maximum frequency minus something.
Yeah.
Okay, so maximum frequency is 300 and maximum frequency minus uh, yeah, okay, yeah, okay,
Yeah.
okay,
So it is not, yeah. So 100 we anyhow will not get 100. So you try to just understand using a drawing spectra, then you can understand, or else you have
yeah.
understood the
No,
problem.
no, 1 minute. Can you draw the spectra once again? I'm just making notes.
Okay, okay, yeah. So MF you have 300, 300. I think it is sine now. Cosine, cosine. So cosine you'll have this one. Then MSF, MSF, which Fs is equals to, what is that? Fs is 500. Then this frequency will go to 500, and 500 plus 300 is what? 600. 500 minus 300 is what? 200. Similarly, if you have 2Fs, I'm making positive 2Fs, which is 1000. Then 1000 plus 300 is what? 1300. 1000 minus 300 is what? 700. And then you will have a only n is equals to 0, then only 300, 300. So this type of sector you will get, sir.
Okay, okay,
Yeah, so when n is equals to 0, you will have this. When n is equals to 1, you will have this one. When n is equals to 0, you will have this one. Wait a second. When n is equals to 0, you will have this one.
okay.
And
When when n is equal to 1, we
uh,
have,
when n is equals to 2, you will have this.
okay, only when n is equal to 0 that it has both negative and positive. Okay, okay. N equal to
Okay.
2, right, right. Okay, ma'am.
Yeah. Yeah. I made it wrong, I think. Yeah.
Okay.
Okay. So, ninth question. So, consider band limited signal sample at a rate greater than Nyquist rate. The original signal can be considered from the sample via interpolation using.
Can the weak
Which one?
So a band limited signal we have which is sampled at the rate greater than Nyquist rate we saw, which is MSF. The original signal can be reconsidered from the samples via interpolation using,
Simple, ma'am.
yeah, sync pulse. So this is also equalization.
Okay.
Equalization is nothing but a filter which is a have sync nature. Okay. So last question. The what is the minimum sampling rate required to avoid aliasing for the signal MT is equal to sync for pi t? Yeah, 4 power pi t.
Ma'am, 20 hertz.
Yes, it's simply the multiplication of 4 into 5.
Yes,
Yeah,
yes. I think you already shared formula n multiplied by m.
yeah. And that is a homework for how we will calculate
Ma'am,
pi
this
t.
spectra will be trapezoidal sort of. We are actually convolving two triangular pulses, right? Two triangular signals. So
Okay. Convolution of triangle, rectangle will have a triangle.
triangle
The convolution
and
of
two
triangle,
triangle.
triangle will have trapezoid. Yeah.
Okay, ma'am. Okay, ma'am.
So yeah. So answer is this. N into Fs, which is 20 hertz. So okay, we have solved this question. So I think we can quit this class. I think yeah, recording has done. So thank you for joining, and thank you so much for listening to the class. So we will meet in the next. Yeah, question.
Ma'am, actually, regarding my gate score and this IT, I'm going to choose. I had some questions, so can I mail you about those questions?
Yes. You can mail. I'll
Okay,
give
ma'am.
you my preferences. No issues.
Yes, ma'am. Actually, I'm having some typical question. You can actually answer those questions, right? So it is a big step for me, actually. So,
Okay. No issue then.
okay, ma'am. Okay,
Okay.
ma'am.
Yeah.
Ma'am, can I have that email ID? I don't remember actually.
It is there in my YouTube.
Okay, ma'am.
It is there in my YouTube.
Okay,
So
ma'am. Okay, ma'am.
yeah.
Okay, ma'am. Okay, ma'am. Thank you.
Okay. Yeah.
Okay, madam. Thank you. Thank you.
Yeah. Thank you so much. Okay.